Imagine you are standing on a steel deck the size of 3 football fields, surrounded by nothing but open ocean in every direction, and the nearest port is 11 days away at full speed. There are 5,000 people living inside the hull beneath your feet. They need water, they need food, they need air, they need electricity, they need functioning medical equipment, sewage processing, communications, and a command structure that never sleeps. Now imagine that every single system keeping those 5,000 people alive was designed not to be impressive, not to be cutting edge, not to be the most advanced version of itself, but to be the one thing that will not fail. That is the central philosophy of every aircraft carrier ever built. And it is a philosophy that most engineers outside of naval architecture have never had to fully reckon with. That in certain environments, innovation is not progress. In certain environments, innovation is a liability. The question is not what an aircraft carrier could do with the most advanced systems available. The question is, what happens to 5,000 people in hostile waters with no external help if the most advanced version of that system breaks down in a way no one has seen before? To understand why reliability is chosen over innovation at virtually every design decision point on a modern carrier, you first have to understand what the carrier actually is. It is not a ship in any conventional sense of the word. A ship transports things. A ship moves from port to port and relies, at every stage of that journey, on a global infrastructure of fuel suppliers, dry docks, spare parts networks, trained technicians, and communication links. A carrier severs all of those connections by design. It is engineered to operate indefinitely, as though the rest of the world has gone silent. If you were living here, if this were your reality for the next 7 months, you would begin to understand that the machinery around you is not performing a function so much as it is replacing a civilization. The water treatment systems aboard a Nimitz-class carrier produce approximately 400,000 gallons of fresh water every single day from seawater. That is not a luxury. That is the baseline. If those systems produce 350,000 gallons on a given day, and they do so for 3 consecutive days, and consumption has not adjusted, you are already inside a compounding failure curve. The engineers who designed these systems understood that a civilian water utility can call a repair crew. A carrier cannot. The system must not fail, and if it fails, it must be repairable using only the tools, parts, and knowledge already aboard. This is where civilian engineering logic begins to break down when applied to carrier design. In civilian infrastructure, redundancy is expensive. A city builds one water treatment plant and relies on the supply chain to fix it when something goes wrong. On a carrier, redundancy is not expensive. It is existential. Every critical system has a backup. Every backup has a backup procedure. And critically, the primary systems are not chosen because they are the most efficient or the most advanced. They are chosen because they are the most understood. A system that 200 engineers in a specialized laboratory fully understand is more dangerous aboard a carrier than a system that is 30 years older, but that every technician in the engineering spaces can diagnose with a flashlight and a set of hand tools. This is the hidden logic that governs carrier design, and that is almost never discussed in popular coverage of these vessels. The older a technology is, the more failure modes it has already surfaced, and the more solutions to those failure modes already exist in the institutional memory of the crew. Innovation introduces failure modes that have not yet been discovered. At sea, in hostile waters with no resupply, an undiscovered failure mode is not an engineering problem. It is a survival problem. The propulsion system is the clearest expression of this philosophy. Nuclear reactors aboard carriers like the USS Gerald R. Ford or the USS Nimitz are not the most powerful reactors ever designed. They are not the most efficient. They are chosen because they represent a technology that has been operated, failed, repaired, and perfected across decades of continuous deployment. The reactor designs used in carrier propulsion have accumulated more combined operational hours than almost any other reactor type in human history. Every anomaly, every pressure fluctuation, every unexpected heat signature, these events have been cataloged, analyzed, and translated into training procedures that are drilled into engineering crews before they ever step aboard. The reactor itself is a known quantity, and that known quality is worth more. In the context of a carrier operating thousands of miles from the nearest support facility than any efficiency gain a newer design might offer. But here is what most people never consider about nuclear propulsion in this context. The reactor does not just move the ship. It powers the entire civilization aboard it. The water treatment plants, the food preparation systems, the medical equipment, the aviation fuel systems, the catapult launch systems on older carriers, the electromagnetic launch systems on newer ones, the communications arrays, the air conditioning, the lighting, all of it draws from the same energy source, which means that the reactor is not a propulsion system with secondary electrical functions. It is a power grid with a propulsion function attached, and the management of that power grid, the constant balancing of demand across thousands of systems and tens of thousands of individual users, is one of the most complex ongoing engineering operations that takes place anywhere on Earth. If you were working in the engineering spaces during a high-demand operational period, flight operations, air defense exercises, full combat readiness, you would understand this in a way that is difficult to convey from the outside. The demand on the power grid during peak flight operations is not constant, it surges. The electromagnetic aircraft launch system on the Ford-class carriers, the EALS, draws an enormous pulse of power with each catapult cycle. That pulse must be absorbed by the grid without cascading into voltage fluctuations that affect medical equipment 2 decks down or navigation systems in the island structure above. The engineering challenge here is not technological novelty, it is system integration across decades of layered technology and thousands of interdependent components. And the lesson the Navy has learned repeatedly through operational experience is that introducing a new high-power system, even a clearly superior one, creates integration problems that are invisible until the system is operating under real-world conditions. The EALS itself became a case study in this principle. It is technologically superior to the steam catapults it replaced. It offers more precise energy control, less stress on airframes, greater flexibility in launch weight. But its integration into the Ford-class power grid created reliability problems that took years of operational experience to diagnose and resolve. That resolution process, that long, expensive, operationally disruptive period of discovering the unknown failure modes of a new system, is precisely what carrier design philosophy traditionally tries to avoid by defaulting to proven technology. Here is what most people never consider. The human dimension of system reliability aboard a carrier is not secondary to the engineering dimension. It is inseparable from it. A system that is theoretically reliable, but that requires a level of technical expertise that only a handful of people aboard possess is not, in practice, reliable. It is fragile in a different way, fragile to attrition, to transfer cycles, to the rotation of crew that happens every few years as sailors complete their service commitments and are replaced by newer personnel. Carrier crews turn over at a rate that would be considered catastrophically high in most civilian engineering contexts. The people who learn the quirks of a particular system, who develop the intuitive diagnostic sense that comes from thousands of hours of operation, are regularly replaced by people who are well-trained but inexperienced with that specific installation. This means that carrier systems must be reliable enough that an experienced crew can maintain them, and simple enough that a less experienced crew can be trained to maintain them within the time available before the next deployment. A system that is only reliable in the hands of 10 people who have spent 3 years learning it is a system that creates an unacceptable single point of failure in the human layer of the engineering stack. And this human layer, the maintenance culture, the training pipeline, the institutional knowledge transmission, is as carefully engineered as any mechanical component. Watch how maintenance cycles are scheduled, how technical manuals are structured, how troubleshooting trees are built. These are not bureaucratic artifacts. They are the engineering of human reliability into a system that cannot afford human failure. The food supply system operates under constraints that reveal this philosophy in a different register. A carrier at sea for 7 months is not resupplied in the way that most people imagine. Underway replenishment, the transfer of supplies from a supply ship to a carrier while both vessels are moving, is a capability, but it is not a daily event, and it is not guaranteed in a contested environment. The carrier's food system is designed around the assumption that resupply may not occur on schedule. This means cold storage, dry storage, and food processing systems engineered for reliability over long periods without maintenance access to the shore-based supply chain. The refrigeration systems must operate continuously in conditions that vary from the Arctic to the equatorial Pacific. They must withstand vibration, salt air, humidity levels that would destroy civilian refrigeration equipment in months, and the mechanical stress of operating in heavy seas. The solution is not the most efficient refrigeration technology available. The solution is refrigeration technology that has been deployed in the marine environment long enough that every failure mode is documented and every repair procedure is understood by the technicians who will be performing those repairs at 3 a.m. during a storm in the South China Sea. This is not a failure of ambition. It is the product of hard experience. Early carrier programs that pushed aggressively toward the technological frontier regularly encountered system failures that were extraordinarily difficult to diagnose and repair in the operational environment. The institutional response, over decades, was to calibrate the adoption of new technology against the operational risk of deploying that technology before its failure modes were fully understood. Medical systems aboard a carrier represent perhaps the most ethically concentrated expression of this philosophy. The carrier operates a fully functional hospital, including surgical suites, intensive care, dental facilities, and psychiatric support, because 5,000 people in the operational environment will experience the full spectrum of medical emergencies regardless of whether a hospital ship is nearby. Appendicitis does not wait for port. Cardiac events do not schedule themselves around underway replenishment windows. Trauma from flight deck operations, one of the most dangerous working environments in human experience, can occur at any moment. The medical equipment aboard must be reliable not because reliability is preferred, but because there is no alternative when you are 2,000 miles from the nearest hospital. And this creates an interesting constraint. Carrier medical systems tend to lag behind the absolute frontier of civilian medical technology by design. A new surgical imaging system that is installed in a major hospital has the benefit of a manufacturer's technical support team, a local spare parts network, a service contract, and clinical engineers who can be called in to troubleshoot. The carrier has none of these. What the carrier has is a medical department that understands deeply and practically the equipment it operates, a system that the medical staff can maintain, calibrate, and repair using onboard resources is more valuable than a system that offers superior diagnostic capability but that requires off-ship support to maintain. This calculus, capability versus self-sufficiency, runs through every major system selection decision a carrier program makes. Communication systems illustrate a different dimension of this reliability imperative. The carrier does not simply communicate. It operates within a layered communications architecture that must function across frequencies, across classification levels, across satellite links, and line-of-sight radio and underwater acoustic channels, in conditions ranging from routine peacetime operations to active electronic warfare environments, where adversaries are specifically attempting to degrade or deny communications capability. The decision to maintain older, proven communications technologies alongside newer systems is not conservatism. It is a deliberate engineering choice to maintain fallback capability across the full spectrum of potential degradation scenarios. If the primary satellite communications link is disrupted, whether by technical failure, by adversarial action, or by the physical constraints of operating in certain geographic areas, the carrier must maintain command authority over its air wing, its surface screen, and its own internal operations, using whatever communication means remain available. This requirement for graceful degradation, the ability to lose capability incrementally rather than catastrophically, means that the communications suite cannot be built entirely around any single technology, no matter how superior that technology is in ideal conditions. The system must work when conditions are not ideal. It must work when the newest components have failed and only the oldest ones remain. The psychological dimension of this engineering philosophy is rarely discussed, but is central to understanding why it persists. 5,000 people living in close quarters in high-stress operational environments for months at a time without access to the stabilizing routines of civilian life require a social and physical environment that creates predictability. Predictability is not a luxury. It is a psychological safety mechanism that prevents the slow erosion of order that occurs when people are uncertain about the reliability of the systems on which their lives depend. When the lights work consistently, when the water tastes the same as it did yesterday, when the temperature in the berthing spaces is controlled within an acceptable range. When meals are served on schedule, these are not comfort features. They are operational requirements. The carrier's capacity to project power depends entirely on the psychological coherence of the 5,000 people operating it. And that coherence depends, at a level most people never consciously recognize, on the reliability of the physical environment. A crew that is managing chronic system failures, that is uncertain about water supply or power continuity or food availability, is a crew that is expending cognitive and emotional resources on basic survival that should be directed toward operational performance. The engineers who designed the carrier systems understood this, even if they understood it intuitively rather than analytically. Reliability is not just an engineering value, it is a human performance multiplier. And so the carrier emerges not as a weapons system with accommodation facilities attached, but as a fully autonomous civilization engineered to survive indefinitely without the modern world. Its design philosophy, reliability over innovation, proven technology over theoretical superiority, self-sufficiency over efficiency, is not the product of bureaucratic inertia or military conservatism. It is the product of hard-earned operational experience accumulated across decades of continuous deployment in the most demanding environments the planet offers. Every system that operates quietly and without incident on a carrier operating in the Western Pacific is the descendant of a system that failed somewhere under conditions that revealed a failure mode that no one had anticipated. The carrier's reliability is not accidental. It is the accumulated engineering wisdom of a civilization that has spent 70 years learning at great cost what happens when systems fail at sea, far from help, with no option but to solve the problem using only the people and materials already aboard. The question that remains, the one that the carrier's design philosophy has not yet fully resolved, is what happens as the gap between proven technology and available technology continues to widen. Every year, the systems that represent the absolute frontier of capability become more complex, more interdependent, and more difficult to maintain without specialized off-ship support. Every year, the operational environment becomes more demanding and the adversary threat more sophisticated. At some point, the carrier will face a choice between the reliability it has always prioritized and the capability it increasingly requires. How that choice is made and what systems will be built around the answer is the engineering question that the next generation of carrier design will have to answer. In deep water, far from home, with 5,000 lives depending on getting it right.